Let's talk about rational root test. We let f of x be a polynomial with integer coefficient, where the rational number r over x is the root of f of x, and the greatest common divisor between r and x is 1, and r is not equal to 0. Then you can say r is divided by the constant of the function, and s divided by the coefficient of the highest degree of the polynomial. Let's solve some example. Let's solve an example. And we are asked to show that the polynomial is irreducible in Q of x, where the function given is 2x raised to the power 3 minus 7x plus 1. So here are the solutions. So first we let the function be 2x raised to the power 3 minus 7x plus 1, where r over x equal to q are the root of f of x, with the greatest common divisor between r and x is equal to 1. Then r is divided by 1 and s divided by 2. Hence, r is equal to 1, and we add plus or minus to 8. S is equal to 2 and 1, and we add plus or minus to 8. This implies that the rational number r over x is equal to plus or minus 1 over plus or minus 1 plus or minus 2 are the rational number. So r over x is plus or minus 1 plus or minus 1 on 2. After that, we substitute these rational numbers into the function. When you substitute 1 into the function, you get negative 4. Negative 1 is 6. 1 on 2 is negative 2.5. Negative 1 on 2 is negative 0.5. Hence, f of x has no root in Q. Hence, by the theorem of f of x is irreducible in Q. Since f of x is primitive, f of x is also irreducible in z of x. Let's solve another example. The same procedure. We let f of x to be our function, and we identify the rational number, where the rational number r over x are the roots of f of x, and the greatest common divisor between them is 1. So we let the factors of r and s. The factors of 2 is 1 and 2, and we add plus or minus to 8. The factor of 1 is 1, and we add plus or minus to 8. Our rational number is plus or minus 1 plus or minus 2 over plus or minus 1. Now, we substitute our rational numbers 1, negative 1, 2, negative 2 into the function. So when you substitute positive 1 into the function, you will get 4. Substitute negative 1 into the function, you will be getting 0. Substitute 2 into the function, you will be getting 0. When you substitute negative 2 into the function, you will be getting negative 20. Since negative 1 and 2 are the root of f of x, then by the theorem, f of x is reducible in q of x, because f of x has a root of negative 1 and positive 2. That's why f of x is reducible in q of x. Let's solve our last example. We are asked to show that the polynomial given below is irreducible in q of x. Let's solve it. So first we let f of x be our polynomial, and r over x is equal to q are our root of f of x with greatest common divisor 1. And we identify our r and s, where r is 3 and s is 2. So after that, you list the factors of r and the factors of s. So let's list the factors of r. So the factors of r are 1, 2, and 3. After that, you add plus or minus to each factors. And again, you add plus or minus 1 to 8. So after that, our rational number, which is r over s, is 1, 2, and 3 over 1 and 2 root, which is r over x. The first number is 1. We add plus or minus to 8. 2. We add plus or minus to 8. 3 to 1 on 2. 3 on 4, 3 on 2. After knowing these rational numbers, we substitute it into the function. So first, we substitute 1 into the function, and it's 24. We substitute negative 1 into the function, which is negative 4. We substitute 2 into the function, which is 125. We substitute negative 2 into the function, which is negative 15. We substitute positive 3 into the function, which is 420. We substitute negative 3 into the function, which is 0. And again, we substitute 1 over 2 into the function, which is 35 on 4. We substitute negative 1 on 2 into the function, which is 0. Substitute 3 on 2, which give us negative 117 on 2. Lastly, we substitute negative 3 on 2 into the function, which is negative 39 on 4. Since the function has a root of negative 3 a negative 1 on 2